Order each set of logarithms from least to greatest. Rewrite the logarithms. Set each logarithm equal to x so we can solve for the result. The first logarithm has no base written, so it must be base 10. Convert to exponential form. This gives us x equals 1. Finding x equals 1 tells us that log 10 evaluates to 1. The next logarithm can be written as 2 to the power of x equals 16. Write 16 as 2 to the power of 4. This gives us x equals 4. Finding x equals 4 tells us that the base 2 logarithm of 16 evaluates to 4. The next logarithm can be written as 9 to the power of x equals 1/3. Write 9 as 3 squared and write 1/3 as 3 to the power of -1. Multiply the exponents. Set the exponents equal to each other. This gives us x equals -1/2. Finding x equals -1/2 tells us that the base 9 logarithm of 1/3 evaluates to -1/2. The next logarithm can be written as 16 to the power of x equals 1/2. Write 16 as 2 to the power of 4 and write 1/2 as 2 to the power of -1. Multiply the exponents. Set the exponents equal to each other. This gives us x equals -1/4. Finding x equals -1/4 tells us that the base 16 logarithm of 1/2 evaluates to -1/4. The next logarithm can be written as 5 to the power of x equals 1. This gives us x equals 0. Finding x equals 0 tells us that the base 5 logarithm of 1 evaluates to 0. And finally, we order the logarithms from least to greatest. Now we'll move on to part B. Rewrite the logarithms. Set each logarithm equal to x so we can solve for the result. The first logarithm can be written as 1/3 to the power of x equals 27. Write 1/3 as 3 to the power of -1 and write 27 as 3 cubed. Multiply the exponents. Set the exponents equal to each other. This gives us x equals -3. Finding x equals -3 tells us that the base 1/3 logarithm of 27 evaluates to -3. The next logarithm can be written as 1/4 to the power of x equals 8. Write 4 as 2 squared and write 8 as 2 cubed. Write 1/2 squared as 2 to the power of -2. Multiply the exponents. Set the exponents equal to each other. This gives us x equals negative 3 over 2. Finding x equals negative 3 over 2 tells us that the base 1/4 logarithm of 8 evaluates to negative 3 over 2. The next logarithm can be written as 1 over 8 to the power of x equals 1/2. Write 8 as 2 cubed. 1 over 2 to the power of 3 equals 2 to the negative 3, and 1 over 2 equals 2 to the negative 1. Multiply the exponents. Set the exponents equal to each other. This gives us x equals 1 over 3. Finding x equals 1 over 3 tells us that the 1/8 base logarithm of 1/2 evaluates to 1 over 3. The next logarithm can be written as 1 over 4 to the power of x equals 1/2. Rewrite 4 as 2 squared. 1 over 2 squared equals 2 to the power of negative 2, and 1/2 equals 2 to the power of negative 1. Multiply the exponents. Set the exponents equal to each other. Divide both sides by negative 2 to get x equals 1/2. Finding x equals 1/2 tells us that the base 1/4 logarithm of 1/2 evaluates to 1 over 2. The next logarithm can be written as 1 over 8 to the power of x equals 1 over 8. This gives us x equals 1. Finding x equals 1 tells us that the 1/8 base logarithm of 1/2 evaluates to 1. The logarithms are already ordered from least to greatest. Now we'll move on to part C. Estimate the order using benchmarks. Rewrite the set of logarithms. "25 is not a power of 3, so we'll estimate using 27 instead, which is a power of 3. 27 is called a benchmark in this situation because we are using it as a convenient reference point. The logarithm can be written as 3 to the power of x equals 27. This gives us x equals 3. Remember, 3 is just an approximation. The actual value of the base 3 logarithm of 25, 2.93, is slightly less than 3. You will learn how to calculate the decimal value of logarithms like the base 3 logarithm of 25 in a later example. In the next logarithm, 7 is not a power of 6, so we'll estimate using the benchmark 6 instead. The logarithm can be written as 6 to the power of x equals 6. This gives us x equals 1. Remember, 1 is just an approximation. The actual value of the base 6 logarithm of 7, 1.09, is slightly greater than 1. In the next logarithm, 1 over 15 is not a power of 1 over 4, so we'll estimate using the benchmark 1 over 16 instead. The logarithm can be written as 1 over 4 to the power of x equals 1 over 16. Write 4 as 2 squared, and write 16 as 2 to the power of 4. This gives us 2 to the power of negative 2x equals 2 to the power of negative 4. Set the exponents equal to each other. This gives us x equals 2. Remember, 2 is just an approximation. The actual value of the base 1/4 logarithm of 1 over 15, 1.95, is slightly less than 2. The next logarithm, the base 8 logarithm of 3, could use both 2 and 4 as benchmarks. If we use 2 as the benchmark, we get x equals 1/3. If we use 4 as the benchmark, we get x equals 2/3. The average of these fractions is 1.5 over 3. Reduce the fraction to get 1/2. Remember, 1/2 is just an approximation. The actual value of the base 8 logarithm of 3, 0.53, is slightly greater than 1/2. And finally, we order the logarithms from least to greatest.